So this is going to be a relatively short screencast, but it's one that introduces an important concept. It's a concept that's going to come up over and over again as we move forward and talk about weather. And this all ties back to this notion of how pressure is related to the weight of the air column. We've talked about this quite a bit. I've said it over and over again, pressure, weight, pressure, weight, pressure, weight. Wait, what? So in this case, what I want to do is I want to take this idea of how pressure is related to weight, and I want to pull in density and how density is related to temperature. And ultimately, the way this is going to be expressed is by talking about pressure surface heights and the heights, so the heights of a pressure surface. So you'll recall back a couple screencasts ago, we introduced the notion of a pressure surface being a surface along which pressure has the same value everywhere, say 500 millibars. And the last screencast, we talked about troughs and ridges on the pressure surface. The idea being that some places this 500 millibar level is higher above the ground, so that's a ridge, and some places this 500 millibar level is lower, which is a trough. And of course, we were just using 500 millibars as an example. We could pick any value of pressure and make the same arguments. So we could have said 200 millibars, for instance, or 850 millibars. Same idea. Okay, so how does this work? So first, I'm just going to go ahead and state the rule, how the heights of the pressure surfaces are related to the temperatures. And then after stating the rule, I want to go back and try to figure out why it is using what we know about pressure and how it's related to weight. Okay, so first the rule. The rule is this. As a rule of thumb, so this isn't 100%, but it's a pretty good rule. It's pretty close to 100%. Locations that have warmer temperatures in the lower troposphere, so warmer temperatures in the lower troposphere, will be associated with, so they're associated with higher pressure surface heights, so higher pressure surface heights at upper levels. I.e., if you've got warm air down near the ground in the lower troposphere, then typically your pressure surfaces at upper levels will be higher. They'll be located at higher altitudes. I.e., where you have warm air near the ground, you tend to have a ridge. On the other hand, if you have cold air near the ground, then your surfaces will be located at lower altitudes, i.e. you tend to have a trough. Okay, let's see if we can go through and piece together why this is using what we know about pressure and weight. So let's say we go through and make a little cross-section of the atmosphere. So this is going to be a vertical cross-section down here. You can say maybe we're looking west towards Austin, in which case you've got south to your left, and you've got north to your right, and this is up and down, right? So we're looking towards the west, south to our left, north to our right, and then up and down. And let's just suppose that down here in the lower troposphere, it's I'll get back to that, jumping ahead here for a second. So first of all, let's just note that down near the ground here, the pressure is always pretty close to 1,000 millibars, right? The standard pressure, the average pressure was 1,013, and it can vary a bit either way. It can vary 20 to 30 millibars either direction. But even so, the typical changes in pressure are at most a few percent. So to within a few percent at least, the pressure down here near the ground is pretty close to 1,000 millibars. So just to make things simple for our argument, we'll just say the pressure everywhere down here on the ground is 1,000 millibars. That'll make things easier. Now, for the purposes of our example, let's also say something about the temperature. Let's suppose that the temperature is warmer on one side. We'll put it over here to the left, which we've been saying was south. And then it's colder on the other side. And just to be clear, we're talking about temperatures down near the ground here. So temperatures in the lower troposphere are warmer on one side and colder on the other. Now let's suppose we start over here on the right where it's colder and we go upwards above the ground until the pressure drops to 500 millibars, i.e. we're looking for the 500 millibar pressure surface and where it is. And so let's suppose as we go up, pressure drops, and the place we hit 500 millibars is right here. So let's just say it's there. That's where we hit 500 millibars. Now let's say we go over here to the other side where it's warm and ask where we hit 500 millibars there. And so is it going to be higher than it was before? Is it going to be lower? Is it going to be the same? So what's the deal? Well, in order to sort that out, we need to think about pressure and weight again. And one of the things that we inferred from this relationship between pressure and weight is that if we take two values of pressure, say 500 and 1,000, the amount of mass in there in between is always the same. It's always the same amount of mass. It's the amount of mass that weighs 500 millibars worth of pressure, right? Because it's the amount of mass that contributes 500 millibars worth of pressure. So over here on the cold side, there's a certain amount of mass in that layer. When we go over to the warm side, it's going to be the same amount of mass in that layer, the amount of mass that weighs 500 millibars. The only difference is over here, that air is warm. And where it's warm, it expands a little bit. It becomes less dense. So if you have the same amount of mass, but it expands and becomes less dense, then that suggests that the column height here, up to 500 millibars, is going to be higher. So our 500 millibar height must be higher. So over here where it's cold, you've got that amount of mass contracted into a smaller layer, a thinner layer. Over here where it's warm, that mass expands into a thicker layer. In between the two, there's going to be some change, right? Some change from warm to cold. And as you go from the warm side to the cold side, well, on the warm side, everything is expanded in the layer and things are higher. On the cold side, things are contracted, and so the layer is thinner. And so you're going to have some transition in between, so it might look something like this. And just to sort of reinforce this visually, I'm going to go ahead and put some colors in here too. I'm going to sketch it in as red over here where it's warm and blue over here where it's cold. Okay, so this basically is where this rule comes from then. The basic idea here is that in this layer between 1,000 and 500, there's always the same amount of mass, but over here where it's cold, the layer contracts, and so it becomes thinner, and over here where it's warm, the layer expands, and so it becomes thicker. And so as a result, your pressure surface, the place where you hit 500 millibars, is higher over here on the warm side, and it's lower over here on the cold side. So that's exactly what this rule is saying up here above. So that's basically how it works. So this is the same thing, just where the graphic's drawn in already. And so the idea over here is that you've got a certain amount of mass in your layer, and where it's cold, the column contracts, becomes more dense. Over here where it's warm, the column expands, becomes less dense because it's warm. And so as a result, your higher heights over here on the warm side, lower heights over here on the cold side. Now, one thing that you can infer from this is that on average, there's going to be a difference in height for a given pressure surface from south to north. Because on average, it's warmer to the south, colder to the north, and so as a result, the heights are higher up here and they're going to slope downward as you go to the north. So we can state that by saying that, in general, our upper level pressure surfaces are going to slope downwards from the equator to the pole. They're going to slope downwards from the warm side to the cold side. I'm going to put a little box around this because it's something that's going to come up again and again. In general, your pressure surfaces will be higher over here where it's warm, and they'll be lower where it's cold to the north. And so there's going to be a slope from equator downward to the pole. Now I should note that there's nothing special about the 500 millibar surface here. We could make the same argument for any other pressure surface. We could have said 200 millibars. So again, if we said between 1,000 at the ground and 200, right, there's always going to be the same amount of mass. And it's the amount of mass that contributes, in this case, 800 millibars, because you're going from 200 to 1,000. And so where it's warm, it would expand, and where it's cold, it would contract. And so you'd get the exact same thing for the 200 millibar surface in that case. You can use any pressure surface you want, and you'll get the same basic idea. This is the book's attempt to illustrate the same thing, sort of in 3 dimensions. And it's the same basic idea. You can see you've got south labeled down here at the bottom of the figure, kind of hidden in the corner. North over here. On the south side, it's warmer, as illustrated by the reds. On the north side, it's colder, as illustrated by the blues. I think they stole that from me. But in any case, over here, where it's warmer, the pressure surface, again, they've picked 500 millibars, is higher. And then where it's colder, it contracts. So it's lower, and so you've got the slope downwards from warm to cold for your pressure surface. This guy's showing the upper level chart we actually looked at before when we talked about troughs and ridges. So this is the 200 millibar pressure surface. And again, what's shown on this plot here, it's just a specific example from some day. I guess I could look and see what day it is here. It doesn't show up in my magnifying glass. But in any case, doesn't matter. It's just the 200 millibar surface on some day. And again, what's shown in the black lines here is the height of the surface above the ground. So the altitude of the surface. So this is showing the height of the surface sort of as a topographic map is what this is doing. So for instance, down here we've got our height contour of 2.2 kilometers above the ground. Here, this guy, so everywhere along this line, the height is 2.2 kilometers above the ground. And then if you go to the north, you eventually hit this one up here where the height is only 11.2 above the ground. So you can see that if you start to the south here and you move northward, we dropped our heights by a full kilometer. We were higher above the ground here, 12.2, fell all the way down to 11.2 up here. And so this just illustrates this notion I was just talking about. Down to the south where it's warmer, your pressure surfaces are going to be higher above the ground. In this case, 12.2 kilometers. As you go northward where it gets colder, your pressure surfaces are going to be lower because the layer contracts, and so the surfaces are located at a lower height. And so in this case, going from south to north, we drop down a whole kilometer in height before we get up here to the 11.2 contour. So the surface is sloping downward from equator side to pole side. A couple other things to note about this, that in general, you've got this transition from south to north. As we go northward, we cross contours towards lower heights, means we're sloping downwards. But you also have the same kind of thing happening left to right here, just to a lesser extent. Over here on this side in your ridge, your contours are higher heights. So these guys have higher values of the height. And as I go over here to the trough, I drop down into lower values of the height. And so it's the same idea. This ridge is higher above the ground, means it's probably associated with warmer air below where it expands. And this trough is lower to the ground, which means it's probably associated with colder air below, so it contracts. The second thing I'll point out about this is foreshadowing for later, is that if you look at the contours, you can see that the contours tend to be contracted into this one particular place here. So for instance, right across here, as we go northward, we cross a whole bunch of contours right at once. So the heights are pretty high on this side, and then really quickly we drop off to lower heights. And then after that, we still drop off to lower heights, but much more gradually as we go northward. The reason for that is because the temperature gradient is also going to be contracted. Over here it's very warm, and then there's a very strong gradient to the north, and then all of a sudden it's cold. And so as a result, the heights are very high over here where it's warm, and they drop off very quickly to on the cold side. Basically what this is going to be moving forward is this is going to be a front. A boundary between warm and cold air is going to have this effect at upper levels. Okay, we'll see that idea again. If that didn't make much sense, we'll see it again. So don't get hung up on it at the moment, because we'll come back to it. Okay, before we close this off, I just want to point out that this idea can have important consequences if you are flying in a small plane. Because it turns out that a lot of small planes, although they have altimeters, they have instruments to measure height above the ground, those instruments aren't directly measuring the height. There's no way for them to do that in most cases. What they're really measuring is the outside air pressure. And then knowing something about how air pressure changes with height, they try to estimate the height. So they're not directly measuring the height, they're just estimating height based on the air pressure. What that means is that if you fly along at a particular value of air pressure, say in this case 700 millibars, as you fly along at 700 millibars, say a 700 millibar pressure surface, your altimeter is always going to say you're the same height above the ground because the altimeter really just measures the pressure. And if the pressure is always 700 millibars, it's going to estimate the same height all the time. So it's telling you, for instance, that maybe that you're 10,000 feet above the ground. But in reality, based on the argument we just gave, we know that sometimes the 700 millibar level is going to be higher above the ground where it's warm, and some places it's going to be lower. So even though your altimeter doesn't know about that, it's saying 10,000 feet. Really, you might be a little higher than 10,000 feet at the start, and as you go into the colder air, you might drop down below 10,000 feet. So it's really important to be aware of that, especially if you're flying in mountainous areas, because your altimeter might be telling you you're 10,000 feet, but if you fly into a region where the temperatures are cold, then your pressure level drops way down, and you might end up being lower than you think you are, lower than your altimeter thinks you are. And so as a result, you might think you'll be high enough to clear that mountain, when in reality you're not. And so you slam right into the mountain. Say if you have low visibility and you're just flying by the altimeter, you might ram right into that mountain. This happens all the time. So, well, maybe not all the time, but there are some number of airplane crashes every year with small airplanes where the pilot thinks that they're higher than they really are, and so they end up crashing into a mountain. There's a little phrase that goes along with this, a little motto to keep this in mind. This is something that my Air Force cadet students taught me. It's called high to low, look out below. The idea is if you're flying from regions of higher temperatures to regions of lower temperatures, well, then you have to be aware that your altimeter might not be telling you the real height. It's telling you it just is trying to estimate based on pressure. So you might start off higher than you think you are, and you might end up lower than you think you are. And so you have to be careful about that so that you don't run into obstacles. Okay, so we'll stop here with this idea. And like I said, this will come up again when we start thinking about how weather systems work.